get going. All right, now we're on YouTube, so there we go for the thumbnail, and let's just get going. I have a question about the master theorem. Okay, let's see. Is this theorem used to find big O or big theta? So that's a really complicated question to answer. Technically speaking, it's big theta. However, it's also big O because when you think about big theta includes big O. So, you know, if you've noticed, one of the things that I didn't show in the master theorem is when you get a recurrence relation, you don't give it a base case because you make an assumption that the base case is 1. So it technically is theta because of that assumption, even though, as you see, we're not getting the exact answer. Because like the one that we get with the recurrence relation the math way, that's 100% theta, like 100%. But technically this is theta too. A base case is required always, yes. However, master theorem makes an assumption about that base case. That's one of the assumptions you have. That's like a compromise you have to make. The assumption is that T1 is equal to 1 usually. That's the assumption you have to make. And by the way, if you ever get a recurrence relation on a test or in life, I guess, and they don't give you a base case, that's an assumption you can make, that the base case is 1. Or both 0 and 1 are just 1, okay? And so because of that assumption, and because of the way that the master theorem works, it technically is giving you theta, but for your purposes, it's a big O. Because if you do it by math and you get the real answer, that's definitely a theta. But when you simplify it into big O, which is kind of what you're getting there, so it's like a little bit of both, see? So, you know, I wish I could give you a clean answer, but you kind of have to understand, like, we have to spend like weeks on master theorem to really understand why that's the case, okay? But for the simple terms of this class, when you're writing your solution with the master theorem, either one I will take, if you put a no or a theta, okay? If you're doing it by hand, however, if you're doing the math by hand, that's a theta for sure. And then when you simplify it and you say like 4n plus n log n, that's just going to be O of n log n, that is definitely a big O, okay? So hopefully that kind of gives you the half answer of that. So, yep, okay. Moving on from the master theorem, you will never see it again in this class until you get to 477. So again, that's CS 477. If you're doing a BS, then you have to take that class. You're required to. If you're doing a BA, I don't think you have to take it, but I would encourage you to take it as one of the electives you get to take. So that's to be continued, I guess. Okay. So, yeah. All right. So we're finally done with this recurrence stuff. So from here, the class is easy, or at least it's a lot easier, I would say. There's not that much math involved. You don't do any coding, I think, in algorithms class. In fact, after this class, the only classes that I know for a fact that you will do coding are 326, which you code in different languages, or you code the project in Java, depending on who you take it with, and then compilers. In compilers, you get to code in Java, and you get code a lot. Like you get to code thousands upon thousands of lines of code creating the Java compiler, I believe. So, well, Java, it's not compiler because it's interpreted language, but you know, taking the Java code and converting it into Java bytecode. So, yeah, Espresso. Yeah. Thank you. That's the right name. So yeah, you get to do that, and that, you know, I got to do that. I got to do that, and it was fun, but it was a lot of work. I will not deny that. And there's a lot of weird edge cases. My code was very patched up to get that going, so don't feel bad if it's very patched. As long as it works, you know, doesn't matter what's behind the hood, I guess. So, yeah. But you get to do those with the teammate. So pick a good teammate. That's big important advice. Like, don't just pick your friend that you like, and no. Pick someone that's good. Like, analyze the person, study them, see if they're a good worker, and then do them. That way you don't end friendships over a class. Yeah, I had to do it alone though, because I was taking it as a graduate student. So they're like, nope, you got to do it alone, and you got to do the extra stuff that normal students don't get to do, which made even more work for solo. Yay! But I got it done. So yeah, but yeah, if you don't want to end friendships, you definitely rather do it with someone that you think is good versus like a friend that you know, you still want to be friends with people afterwards. So yeah. Okay, so going back into our easy stuff compared to that, at least. Today we're going to mostly focus on linked lists, but I put sex in the race in case we get there. We might. And so this will be a good example of how the rest of the course is going to run, pretty much, where we're going to talk about some sort of data structure or algorithm, and then I'm going to give you the basics. We'll look at the time complexity and space complexity and whatnot. All the recurrence relation stuff I said applies for space too, by the way. It's just we use it for time most of the time. So, but yeah, so it will all apply, okay? And so yeah, this is literally how the rest of the semester will go. So let's get going. So let's start off by hopefully the reason why we start with linked lists is because this is hopefully a review from 202, where you coded a linked list. You probably coded a double linked list, and so now it's just going to be you refreshing your mind. So we're going to be doing everything. Let's start with the simplest one, though. Let's start out with a singly linked list. Okay. So again, I'm really not going to write much code unless there's a particular thing that you want me to show you code for. I can, but this stuff is hopefully at this point it's review. So I do have at least some code over here to save some time of writing a node, right? So let's start out by refreshing some terminology. That's actually a good starting point. So if you remember, a linked list is made up of nodes, okay? And the nodes are going to be these little squares that you're looking at here, okay? And so they're chained together, and the idea is that you can contain information that would otherwise be stored in something like an array. And so why would you store it in a linked list? Well, there are some pros and cons to an array and a linked list. So let's go ahead and list those here, okay? Think about the three things I said on like day 1 or day 2 of this class that we care about. We care about, when we're talking about an abstract data type and a data structure, the three things we care about in terms of space and time are insertion time, or insertion space required, so insert, retrieval, and deletion, right? So we want to put things in, we want to take things out, and we want to be able to remove things. And here's the trick though. This retrieval stuff, it's not just about removing something, but we may want to remove it in a certain order. So for example, if we want to sort things into like an alphabetical order, and we want to retrieve things alphabetically, that would kind of fit under the retrieval category, okay? You install AdBlock. That's kind of messed up. I'm sorry about that. I think that that only happens when you join though. I have no way of turning that off though, which sucks. But yeah, so you have insertions, retrievals, and deletions, okay? So that's what we care about with any data structure. And of course, we care about this in terms of time, primarily these days, but space is something to think about as well. In the case of linked lists, it is something actually that we'll consider, okay? But for now, let's focus on time. So what we're going to do is we are going to split this even further into 2 columns like this. In fact, it's too late. We'll go this way. And then we're going to go ahead and list the pros and cons of a linked list in comparison to an array. Okay? So pro and cons. So first of all, we have to understand that a linked list and an array are both able to store the same type of information. So you can store different kinds and doing trickeries, but we're just talking about a homogeneous data structure. Homogeneous standing for everything being the same. So that means that we have all integers, all floats, that kind of thing. You don't have to do that. There are ways around that. There's also ways around that with arrays, which are nasty and not recommended. But the point that I'm trying to say, or if you use polymorphism, it's not as nasty. What I'm trying to say is that you keep data that is the same type, okay? So when it comes to insertion, it turns out that it matters what kind of linked list you're making. So for now, we're going to talk about a singly linked list, which is the most basic, which is kind of what you saw here. And let's just talk about a unsorted singly linked list, so where you just dump things inside that you want, okay? So with that in mind, the advantage of insertion when it comes to a linked list is that you never have to worry about space, right? You can just keep throwing things in and you will never fill it up, unless you, of course, like completely run out of memory, right? But in theory, in a theoretical standpoint, like if you forget about an actual computer and you have a computer that has infinite space in memory, then in that computer, you don't really have to worry about ever changing the size of a data structure, such as you would with an array, right? Because with an array, you have to define a specific size and say, I want to make an array of size 10. Whereas here, you can just keep inserting and not have to worry about that. Now, of course, you can resize an array. That's kind of what vectors do. They resize dynamically allocated arrays, but that is overhead that is required, and that's going to take time. And furthermore, with an array, because you have to give it a fixed size, unless you're making it exactly the required size, which doesn't tend to happen. Typically what you do is you resize an array by increments of like some power or some number. And so you end up with requiring extra space that is probably not being used currently, so that you don't have to keep resizing every single time you insert one element. You make that compromise. With the linked list, there is no need for such a compromise, okay? So the pro is that you can insert fast and not worry about space. Okay? In terms of cons, I wouldn't say that there is any con to inserting in a unordered linked list. However, there is a con when it comes to insertion time if you're trying to insert in a specific spot or a specific index in a list. When it comes to an array, you're looking at an array. If you want to replace a number, so let's say you want to replace the 5th item in an array, all you got to do is provide the index. So you can say, if your array is called A and you want to replace the 5th spot, that's going to be 4, right? Because you start from 0, so 0, 1, 2, 3, 4. And so you just say replace that with 20, assuming this is an array of integers. Okay? So with a linked list, however, you can do this, but you can't do it immediately. It's an instant direct access thing with an array because you know exactly the memory location. What ends up happening with an array, if you ever dereference an array, if the array is called A and you do ampersand A and you see out this value, you're going to get some hex address. How to find out where spot 5 lives is you basically add that in hex to this. So, it's 4 times 4 is 16. So you add 16 in hex, which just means add +1 in this level. So that address would be, my hex is a little rusty, but I believe that that's what it would end up being, 1150. Okay? So that operation, the simple math operation, is instant, and it's a constant time. It's constant, okay? That's the time complexity is constant. Same with this. This is constant, okay? That's big O, omega, everything is constant in this case. Here with the array, it's constant. But with the linked list, it's not. Because the linked list, you only have pointers to the beginning of the linked list, which we call the head pointer. And sometimes you also get a pointer for the tail. That's it. You don't get pointers everywhere else. Otherwise, you would require to have, if you have n number of items in your linked list, you would have to have n number of pointers in the linked list. So that would defeat kind of the purpose. Because where would you store those? In another linked list? That doesn't do much. You store it in an array, then you might as well store the whole thing in the array in the first place, right? So there isn't a pointer that can get you there as quickly, and there's no math you can do because the implementation of a linked list in a language is just allocating memory, allocating one of these nodes, each of these nodes one at a time. And so in your main memory, what that might look like is something like this. So here in main memory is one of the nodes. That's like node 1. And then here's node 2. And then like in the middle might be node 3. and then like way somewhere else down in memory, like I don't know, like another stick of RAM, or somewhere like way down in the other thing might be like node 4, and then like here's node 5, and they're all over the place. And so your pointers are basically going like this, like that, and like that. And so there's no easy math way to say, well, if I'm here, then I know for a fact that the next thing is going to be like somewhere else. No, because it's random. It's random. Well, what's pseudo-random in the sense that like there's no stipulation. You just ask the operating system like, hey, I need some allocation of memory with new and delete, you know, and so it just picks something for you. Okay. So we have a question that says, wouldn't you need a separate function in order to sort the linked list? Depends. If you're doing a unordered linked list and then you wish to sort it, then yes, you make a new function. However, you can also create what's known as a sorted linked list, in which case, as you insert, you would sort at that moment. And that is using something kind of like insertion sort, which we'll talk about when we get to sorting. But regardless of which of the methods you do, you can insert immediately. It's just a matter of deciding where to insert that would slow it down. And that would be the same thing in an array. In an array, if you want to use something, if you want to create a sorted array as you insert, then you have to identify where you have to put it in. So if there's no advantage or disadvantage compared to a linked list there. Similarly, when you're running a sort function, because there it's all about the sort, which again we'll talk about later. But anyways, the con that I'm trying to get to is that whereas with an array you can insert things immediately, you can't do that with a linked list if you're trying to insert in the specific spot of the array or the linked list. So if you're trying to insert at the 5th element, what you need to do is you literally need to traverse this. So you gotta start here and go through the pointers, which takes time to reference those pointers and go there, get to the 5th spot, and then throw it in. Now here is the advantage. So there's a silver lining in that. When you get to the spot where you want to insert, all you gotta do is play around with the pointers, right? So like, to refresh your mind, when we have a linked list like this, where we have 2 nodes that are amongst other nodes, so there's nodes over here and there's nodes over here, okay? And so let's say we want to insert something right here in the middle. What we need to do is, first of all, we need to take this pointer, we need to copy that here, so that that's pointing this way. The next thing we want to do is we want to take the address of the node we just made, which we probably have pointing right now with a temp pointer, and we want to copy that and assign that to wherever this is pointing to, so it points this way. But be careful, if we do that, we lose this link, okay? Which means that now this temp thing is pointing this way, so it's pointing like this. So I'm just going to redraw it to do this. And you have to be aware that when you do that, though, that, you know, as you delete this, that you do that in this order. Because if you delete that line here before you copy this one, then you're going to lose access to the rest of that. So you got to make sure you first copy this and then this, okay? For deletion, you also have to be careful about the order. With deletion, you know, you ideally want to replace this pointer to no longer point to this node, but instead to point here. But if you do that immediately, then you lose this, which means that you have a memory leak. So what you need to do is you need to copy that somewhere into a temporary variable and say, okay, copy this into here. And now go ahead and take this and copy it here. So we can copy that, like literally take this and make it copy there like that. So then go ahead and use this temp pointer that we've made, because now this has been lost, to call delete on that, which will then deallocate this. And then you can just, you know, set that pointer to null or throw it away or something. And you're good to go. Okay? So that's how you insert and delete. That operation is also quick, it's constant time. And you have the ability to insert in the middle. Whereas with the array, you can't do that. You have to shift things around. Like if you have an array with 1,000,000 items and you have to, you know, change something right in the beginning, that's the worst case scenario. That's going to be your big O. It's going to take n time because you have to shift things n times forward. You know, forward. Everything was to be shifted by once to put something. What would be the omega in that case, though? The omega would be that you can insert something at the end of the array, and that's not as bad, especially if you have some space because you just throw it in. If you have to reallocate and you have to copy everything over, that also takes some time. So let's understand that, since that's the first time that I say things like that. What I say when it takes n time is that I have an array, has like a 1, a 2, a 3, and a 4. But there is an empty spot. If I want to insert something into that array, I can just throw it in here, and that is going to literally just take me, you know, I probably have a pointer that, not a pointer, but like an integer that contains the index of the top, kind of like I would in a stack. And that, you know, that has something like int t for top is equal to 0, 1, 2, 3. And so I know that the next spot available is 3 plus 1. So that will take constant time, which we can just say is something like O of 1. Okay? However, suppose that I need to insert something at the beginning. Well, in that case, I gotta shift everything forward, so I gotta delete everything, you know, and then basically bubble it up like that, and then put it in. That means that I gotta take the n number of items in the list and move them. So that's gonna take O of n time, okay? Both of these scenarios represent the same thing, which is inserting a value. So when you're trying to decide how efficient something is or the time complexity, you have to look at the best and worst case scenario. So this is really going to be your worst case scenario, your upper bound of like how bad things can get. And then really this can be represented as your omega, because that's how good, you know, the best case scenario per se, which is like, okay, I just got to throw it in at the end and I got some space. Obviously, if you have to copy things over because you don't have space, like you have something like this and you got to insert a 5, then you got to copy everything over. So that one, regardless of whether you're inserting at the beginning or at the end, is always going to be O of n because of the duplication process, right? So that's how you analyze these things. You start thinking like that with this O of n and, you know, O of 1 or omega of 1 and so on. Okay? And so when it comes to time complexity for insertion, we can say that for a linked list is O of 1, and then that is going to be for an ordered list. However, if you're trying to do an ordered list, then that is potentially going to be O of n. And the worst case scenario being the second to last item is the one that you gotta insert into. Okay? Because the last one's not bad. We have the tail pointer. So if we need to throw something in here, we can just build it here and then update that by updating the tail pointer, you know, and changing that to be here. So that's not a problem. The problem is if it's the second to last, because that's the real worst case scenario. Unless, of course, you have a double linked list, in which case the worst case scenario is right in the middle of the thing, which would take the size divided by 2. So that would be an O of n divided by 2, which we know belongs just to O of n. So still the same scenario. Okay? So that's your insertion. Let's talk about retrieval now. So with retrieval, you know, we go into sort of the opposite of the pros and cons here. So with the array, if you want to access a number in the array, first you got to locate it. That's going to take the same amount of time regardless of which structure you do, which potentially, if it's unordered, is going to take O of n. Let's understand why that's the case too. So if I have a list of numbers, whether it's a linked list or an array, and it doesn't matter what's in them, in fact, I don't know what's in them, let us say that I am looking for a number x, okay? And the way I'm going to search is I'm going to search from the beginning. So I'm going to start looking here, and I'm going to work my way all the way to the end until I check this. So worst case scenario is going to be what? Well, the worst case scenario is going to be that the item that I'm looking for is not even there, right? Because the only way that I can guarantee and say, hey, this thing you're looking for is not here, is if I check every single spot, every single question mark. I have to flip around and see what's there. And once I finish checking them all, I say, hey, you told me to look for 5, but there's no 5 in here. That's the worst case scenario. What's the best case scenario? The best case scenario is going to be that the first card that I flip, the first one here, that happens to be the number I'm looking for. That's like, hey, it's my lucky day kind of thing, okay? So when you're looking at the asymptotic complexity of that, in the worst case scenario, it's going to take n time because you have to look at the entire list. Now remember, n is equal to the number of items in the list. What's the best case scenario? The best case scenario is going to be that what I'm looking for is the first one that I find, which is a constant time, okay? On average, what's it going to be? Well, on average, it's going to probably be that the number I'm looking for is around the middle, which is still going to be O of n, because again, it's going to be something like O of n divided by 2, which is just belonging to O of n, with a constant. So if you want to do your little certificate thing I was talking about with the m and the k and all that stuff, you just say like c is equal to 1/2, n is greater than 1, and that's it, right? So that just basically tells you that, yes, I can make the simplification into that. So ultimately, this is why something that you need to search in linear time takes O of n. And so, that doesn't matter whether you're using a linked list or an array. We are going to talk about data structures that allow you to improve that search time, of course. The most basic thing that you can think about is if you have a sorted list, then you don't have to, and you know that it's sorted, then you don't particularly have to search in a linear fashion. You can use something known as binary search. So what is binary search actually? I'm going to really briefly just go over this, and then you can look it up on your own later. Binary search is a method of searching through a sorted list. So if you have a sorted list, meaning I have the numbers like 1, 5, 10, 12, 18, and 21, and let's say that I'm looking for the number 5, okay? Actually, that's not a good example. Number 18, let's look for the number 18. If I was doing in a linear search fashion, I would just go all the way here, and it will take practically almost O of n to see that the 18 is there. The way that binary search works is the way that we humans tend to search for items on things like a dictionary, back in the day when paper existed, in last millennia or something. All right, so what we would do is we would take a book, so like prop number 1, book. And then if I want to search for something in a dictionary, I open it in half approximately and see what letter I'm at. And if the letter that I'm looking for is less than that, then I've already basically split the number of things I got to search in half. Because I know if it's on this side of the book, then I don't even need to look at any of this. I can just look at here. What's the next thing I can do? Well, I could try going page by page, but that's not going to get me anywhere fast. So what I can do is the same thing. Split it in half, so approximately here. And then now see if the letter I'm looking for is less than this. If it's less than this, then all I got is this stuff to check. If it's greater than that, then it means it's in this section here, which is still in 2 checks. I basically narrow it down from like 100 pages to about 25 pages to look through. If I do that a couple of more times, then I'll be pretty much done. In fact, how many times would I have to do it? That's a simple math problem. You just have to say log base 2 of 100. What is that equal to? Well, 2 to the power of what is this? Probably somewhere around 8. Is that 8, 7? I think 8.5. Let's plug it in here and see on Google. So log 100 base 2. Nope, not log 2100. 6.64. 64. What that means is that I would have to do 7 checks to identify the page where the word that I'm looking for in a dictionary is. Or if I have 100 numbers, I would have to do 7 checks to locate my number. Compare that. Let's think about that. If you do linear search with 100 numbers, you have to search from beginning to end for a number. It's 100 checks. Here, I just have to do 7 checks because I'm just splitting it in half each time. Now, what is the time complexity of binary search then? Well, the fact that I got the word log in there is probably a pretty strong hint that it takes log of n time, which is a lot smaller than O of n. And we want small because small means that it grows slower, which means that it is faster to look through. Okay? So that's basically how binary search works. Now, of course, when you're coding it, binary search can only really be used in an array data structure because you run into the same problem that you run into in linked lists with like indexing stuff. With binary search, you start looking right in the middle, which let's just add one thing here to make it easy. 11 is the middle. So then you know that you check these indices, and then you got to find the middle of that. So you can just do that by dividing the index of this by half, right? So then this is obviously easy to divide, but if it's not, you plus 1 or minus 1. So then you can identify this index, right? So this is index 0, 1, 2, 3. So 3 divided by 2 is just going to be 1.5, but because you integer division, you get a 1 out of that. So that's how you get there. So you can then immediately jump to that spot in the array, right? With a linked list, you can't do that because, again, you can't jump immediately to an index, so you kind of lose like some of the advantages and benefits of binary search. So binary search is really more meant for things like arrays, vectors, that kind of thing. But anyways, assuming that you can do it, then you can identify things in log of n time, which is a lot faster than n time, okay? So already there you see that it matters which algorithm we use to search for things. So there is a catch though. You might be like, well, this is always fast, why don't we just always use binary search when we're storing data? Well, the catch is this. The data has to be sorted to be able to use binary search. And sorting the data takes time. That takes time too. In fact, when we talk about sorting next week or the week after, not probably next week, we will basically figure out that as cool as sorting is, the fastest sorting algorithm out there that is comparison based takes n log n time to sort, okay? So that's just to sort. And then to that, if you're looking for one number, you have to add log n time to search to that number, right? So if you have 100 items that you have to that you have, and they're unsorted, and you're like, okay, let me sort them so that I can use binary search to use this as one time, and then I'm throwing away the data. Well, that one time is going to cost you, obviously, again, this n log n is much faster than this log n, so at that point the log n doesn't really matter. It's the n log n that defines how slow this is. And so because of that, if you just have one item to search, even though the data is unsorted, you take n time. Whereas here, you take n log n time. So then I'd say, okay, if you're just looking for one thing and you never need to use this again, then there's no point in sorting it. That's going to be slower. Go with the linear search. But if this data, like a dictionary that you intend to use in the future multiple times, then yes, go ahead and sort it first. Or if you don't need to get the data immediately, but you might need to in the future, then you can use the current time that you have free to sort the data so that when the time comes to retrieve the data, you have it accessible in a faster method. And that's going to be the approach that we're going to do with the different data structures that we talk about when like trees and hashes and everything. That, most of the time it's just faster if you're looking for one item to just search for it. And even if it's unsorted, just whatever, just go one at a time and search for it. But that's never the case. Most of the times you have to get multiple information from a data structure. So you want to prepare it to be quickly accessible, or you want to prepare the data structure to quickly receive new data. And so that's going to be the balance that we're going to be talking about, where yes, it might take more time to set up something for quick retrieval, but it's a one-time effort and then you're set. So that's the kind of pros and cons we'll see. Okay? So that's binary search, and that is what we're going to put for retrieve, is that it's going to run into the same issue with the indexing. But the pro is that you can basically, once you have the spot, you can just access it, just like you can with an array once you get the index, right? And then the kind of expands into the delete. So the pro with this is that it's very easy to delete. Is O of 1 to delete. And you just basically remove whatever you don't want and then just relink the data structure, right? That's the pro. An array is not easy to delete. It takes O of n time because you have to jank out whatever you don't want, and then you got to shift everything there, which of course can be ideal scenario is what you want to delete is at the end, so you don't have to touch anything after that. Worst case scenario is where you want to delete this at the beginning, so you got to shift everything down by 1. That's going to take you O of n time, right? The concept deleting, there isn't really any with a linked list again, other than again that indexing, right? You got to find what you're trying to delete, so that is going to take time. But again, that's not pure deletion, so we're not going to mention that. Okay, so that's your linked lists. In terms of code, again, I have a piece of code. Did I paste it yet? I don't think I pasted it, so let me just paste it really fast so that we can refresh. And then I believe you in assignment 3 you will be coding a lot of different things, including a linked list. copy. Hold on, I'm trying to copy it. It's just that it's like on the edge of the page, so it's not cooperating. There we go. So here's some basic code for writing a single linked list node. The node is, of course, what's going to contain the data, right? And then the linked list is just a bunch of these nodes linked up together with pointers. And so here's this is templated, of course, because you want to make your life easy and use templates. So we have a class node, and I recommend that you build a constructor for this that allows you to, pass in when you create the node what the data that you want to store in that node is, right? So you have two components in a singly linked list. You have the data component, and you have the reference or pointer to the next item. And typically, when you first create a node, you want to store the data for the component, and then either leave it pointing to null if it's not pointing anywhere, or make that an optional parameter in your constructor that you can immediately pass in the next spot that it's going to point to. So here I just made one constructor with the data, and so because of that, I initialize the data already with what it needs to store, but more importantly, I initialize the next pointer, which is that reference, to null. That's very, very good practice, because the last thing you want is to create a node and forget to actually initialize it to null, and that's how you get your sec faults and headaches. And again, you better be using debuggers for this stuff, because otherwise it's going to be a pain. Okay? In this case, because it's template, it says T, but whatever it is you're using, you use. Okay? Nothing fancy about templates in this, at least in this very basic example. Just in case you don't remember how templates work, I do have this example here of a templated function. So, actually, not a template function, sorry. Well, it is a templated function, but it's a function that is a member of a class. So if you have a class, if you have a function that is trying to work with parameters that are part of a class, then you got to write the template class T. The class T can also be written as type name T. There is a difference, but it's very minor, and you don't have to worry about it. And then you can access any templated variable. Okay, so that's just a function that exists in the void, but can handle templated parameters. That's the other uses of templates: functions and then classes. This is a class. That's a function. Okay. So yeah, just some basic code to hopefully refresh your mind. I have some other code here. All right, I can show you the insert code. I actually wrote this live last semester, but so if you want to see how I created this code, check out the last year's lectures. I believe that's where they're from. This time I'm not gonna write this code live. There's no point in redoing things I did already. Instead, we could, I focus more on talking about other things. So, but I'll still go over it really briefly. So insertion is the one that gets a lot of people, along with deletion, I would say. And so here is some code to basically insert, and there's also a print. So when you insert, this is all templated, so that's why you see the T there, but it would be an integer or whatever object it is you're inserting. And so the first thing you do is you create your node, you allocate it dynamically. So you have to store that node in a pointer temporarily while you put it in the right spot. So I use the word temp, and that's what this first line of code is doing. It is just creating a node, and notice this. Notice I'm already putting in what I need to insert there, which is what I'm getting when I call the insert function from main or whatever. I say insert 5. And what it does is it allocates a node and already preloads it with the value of 5. Also behind the scenes, because we saw the constructor of this, it is going to set that to null, the pointer, right? Again, that's a good thing for safety. We will want to change that once we hook it up, unless it's at the tail end. But again, you're doing that because you want to protect yourself, so that every time that you create pointers, you initialize them to null, because then you can check them if they're not pointing anywhere valid. The last thing you want is a pointer that has an address stored in the pointer, but it's an invalid address, because you get a sec fault and you can't check if it's equal to null because it's pointing somewhere. It's just invalid. Bad things happen. Okay? So you got a couple of cases when you're inserting into a linked list. Case one is that you're inserting at the beginning of the linked list, so the first item. The second case is where you're inserting in the middle, so between an item before and an item after. And then the final case, actually there's 4 cases. The final case is that you're inserting at the end of the linked list, so it's the last item. And I guess the fourth and final case is that the list is completely empty and it's the first thing you're inserting. And that's kind of a little bit of a special case, just because you have to update your tail and head pointer. So remember, you have the tail and head pointer. So where's my little linked list? So not that one, this one. So you have your head pointing to the first node, your tail pointing to the last node, and then you got your nodes in there. Okay. So when you start out with a linked list, you know, when you initialize that class, you'll have a head and a tail, and they're both pointing to the same thing, which is nothing. Okay. And so, phone call. I'll delete the voicemail. All right. So yeah. Okay. I have to go to the dentist tomorrow, and they're calling, so hopefully they're not canceling on me. But we'll see. Okay. So this first case here is that case where the list is empty. Okay. So we have head is equal to null, and head is only going to be equal to null whenever the list is empty. So that's what we're checking with the if statement. So what we want to do is we want to update both tail and head to point to the brand new node we just made. And that's it. That's all we need to do. That's why you see a return here, because you don't need to set anything else to null, because this has already been set to null. So you just throw it in and you're good to go. This is a temporary pointer that you've made here, so you don't need to delete it or something. So when we do linked lists in your future assignments, do you recommend that we use templates? I believe so. Well, you only really use it once, so you don't have to, I suppose. Unless I make you. I don't think I make you. I don't require it. So, no. But I mean, it's good to make a templated linked list, because then you can use it in the future in general, which is convenient. So, there's that. Okay. Moving on, we have the next case. I'm just trying to see which case is this one. This is probably a case where we're inserting, I feel like it's missing some code. We have some print, insert TD. Oh, I see. This is like the incomplete run. Hold on a second. Yeah, it's missing some code. Let me delete this and paste the rest of the code. Okay, let's get in the rest of the code in there. I was wondering why that function looks so short. Copy. There we go. And let's just get rid of this one. Okay, so this one's got more code, so hopefully it's got all the cases in it. It still looks kind of small, but you never know. Maybe we did just write it like that. Okay, so there we go. So we're here right now in this line. So now we're going to keep going. So now in this case, in this case, this specific scenario is if I want to insert in a sorted linked list. Okay, so what it's going to do is it's going to iterate through the linked list and find out where it's got to go, and then based on where it's got to go, it's going to put it in and then make a decision on one of the 3 cases, where it's the beginning, the middle, or the end. Right? We already talked about the empty case, which it doesn't matter whether it's a sorted or unsorted linked list, but yeah. So in this case, we make a previous pointer and a current pointer. That's very useful when you're working with a singly linked list. You don't have to do that with a double. But the double is just the same as a single. You just have to update one or more pointers, so it's not that complex. If anything, it's easier, at least when you're inserting, because you don't have to keep track of this previous and next stuff. So what you do is you keep going on these pointers until you get to the end of the list, which is saved by a null at the end of the last node, right? So that's why I say, well, current is not equal to node. And at first, I set up my previous and my head pointer to point to the head value, I know there's at least one node here, because if not, I would have gone through that code I talked about earlier. So there's at least one item in the list already. So I'm just inserting it somewhere, either before it or after it. Or if there's more than one, then it could be in the middle of something. And so the way that I figure out if it's the right place to put it is I look at the data of the current temporary node, and I see if it's less than the current data. If it's less than the current data, it means that this node should go before the other one, right? Because like if I have a node here, and this node contains a 5, and the one that I'm trying to insert contains a 3, then if I look at the 5 one and I see that 3 is smaller than 5, then my node has to go before it. It cannot go after, because then it will no longer be of increasing order. It has to go before. So this is going to be a case where I have to insert before. Now it could be that there's stuff before mine, so like I'm not the first thing to be inserted, but it could also be that it is literally the first thing inserted, instead of the one existing already there. So what I do is I take the node after, which is currently pointing with cur, and I update my temporary node's next pointer with that. So that's what's happening in this line. Okay? Now what I want to find out is the case of whether I am inserting at the beginning of the list or I'm inserting somewhere in the middle. I know that I'm inserting before the node that I got put in. So I know there's a node after me, so I'm not at the end, but I could be at the beginning or at the middle. How do I check it? Well, is the current node that I have, the cur node, the one that I'm inserting before, was that the head before? And if it was the head, then it means that there's nothing before it. That's how I know that I'm at the beginning. If it wasn't the head, then that means there's stuff before it. So if it's the head, that's easy, because again, all I have to do is insert it before it and update the head value. So I'm going to go ahead and do that case first. So I say if cur is equal to head, first of all, update the head pointer to now point to my node, and then call it a day, because it's already pointing to one before it. If it's not, then that means that there's something before me. So I'm going to use the previous pointer, which is always going to point to one node before me, to access the previous pointer's next pointer and update that to temp. And that will complete the connections. Okay? The only other thing you should know is that you have to update the previous corner at the end of the iteration by taking whatever you're currently looking at and sending that to the previous, and then updating the current to the next one. Okay? So hopefully this is all review. But I have videos also for the 202 class where I built these linked lists live. So you can check them out as well. Okay? So yeah, that's I think enough code to see for today. So let us go ahead and move on. Double linked list very fast, just to make sure you all remember what that looks like. So you got 2 pointers. So you got your data, you got your next, and you got your previous. But you can call them whatever you want, really. This previous is not the same thing as the previous that I was talking about here, though. Okay, so don't mix that. And then when you build another, when you add another node to this linked list. Whoa, come back down. You just go ahead and update 2 pointers instead of 1. And if you thought that was a lot of work, wait till you get to trees or graphs where you could be updating 100 pointers at once. So that's going to be the fun. So really, linked lists are like the baby steps, because you only have up to 2 pointers. When you're talking about graphs, each pointer is potentially a line, an edge in a graph, and you can have a very high degree of 100 different lines. So instead of keeping the pointers individually by like variables like previous and next, or pointer 1, pointer 2, you're just going to make a list of them, or an array of them, or you can make a linked list to keep the pointers. So yeah. All right, cool. So if I look at your assignment very fast, let me just make sure that I'm not forgetting anything important. You're going to be taking the data from the first assignment, and then you're just going to be inserting it into a linked list, I believe. Yep, so you got to make a couple of data structures. Primarily being a linked list, but you also want to keep it as an array, and I believe I also make you use a vector. So you make the old school array, vector, and linked list. For the linked list one, I don't recall if I make it a single or double. Oh, I say, go ahead and make it a linked list, single or doubly, up to you. So yeah, it's up to you. So whatever you find easier. I think the double is easier, but you know, just because of you don't have to handle this previous situation, it's done automatically for you, and it's very convenient to be able to move back and forth in the linked list, especially when you're trying to like print the list backwards or something. You have to do, otherwise you have to do like recursion. So I think a double linked list is better. But if you just dread linked list and I guess worried about it, then do the singly. But like I said, I mean, when you do the stuff that has like 100 different pointers, you know, a double linked list is going to look like piece of cake. So maybe, you know, it's just one of those things. It just seems like a lot now because you haven't seen what's coming, kind of thing. For the allocating a linked list, it doesn't really matter because ultimately you're just going to traverse the linked list. So you can just do a loop that says like, so you start out by saying, make a pointer, so node temp, and set that to the head. And then you just say while temp next, or just temp. Well, temp is not equal to null, or null PTR, depending on what you're using. So you just do that, and then you just call delete on it. But be careful about how you do that, because while this code will compile, if I just say like delete temp, and then I say temp gets temp next, while this code will compile and run okay, like pretty much every single time, it's technically bad because you're accessing a dangling pointer. Because when you delete this and then you do this, you're technically accessing stuff that's been deallocated. So it's not good practice. It's not good code. So you shouldn't do that. It's nice because it's short and relatively straightforward, but not good to use. So what you want to do is you want to make another temporary variable. So call it temp2, and then store in there temp next. Then go ahead and delete temp as before. And then when you're updating temp, just update it to whatever temp2 has. And so now you never accessed a dangling pointer. Okay, so that one line of code will fix your code. You know, quick fix. Yep, there's not much to it. I mean, be safe though about this, just in case that like. So in theory, you would do all this in like a destructor, but in theory, this should be okay because you're doing a check here that says temp is not equal to null, and that means that this should be a valid pointer to the reference. So yeah, I'll take that back. This is good enough. So yep, wouldn't that crash? Are you talking about the first example before I corrected it? And the answer is no, it wouldn't crash because dangling pointers are bad, but they're not illegal per se. And most of the time, the computer is not going to reuse the memory immediately. So while you should never do it because you're essentially leaving your hands to luck, most of the time you're going to get lucky. So yeah, so don't do it because, like I said, it's dangerous. Dangling pointers are no joke. But at least feel comfort knowing that if you do happen to do it, you're probably going to be okay. It's just, it's like, okay, good example, but really bad thing to say is, if you don't wear a seatbelt, you'll be okay most of the time until you crash and die one day, right? So that's like a dangling pointer thing. You want to wear a seatbelt not because you think you're going to crash and die, but just in case that you do, right? So you wear a seatbelt. But in theory, I guess, if you didn't, you would be okay as long as you don't crash, which the statistics say that it's very unlikely for you to crash. But I don't know about you. I would rather play it safe and wear the seatbelt than leave my hands up to that edge case, right? So yeah, when you think about dangling pointers, think about the seatbelt comparison. And if you like to live dangerously, then I guess, you know, save one line of code and do the other thing. Okay. Because you're dealing with a pointer for a linked list, you just need to delete a pointer. You don't need to call the delete array. concept. That's only if you're deleting an array of things. But here you're just deleting one pointer, so you're okay. See, you guys are taking it the wrong way. I always wear my seatbelt, by the way. I don't play around. But except I guess like no, yeah, because I was gonna say when I was a kid I had a go-kart, but I think I had a seatbelt on it as well. But it was like a really ghetto seatbelt, so I don't know if that would have helped me a lot in the crash. But I never crashed. My dad crashed, and then he destroyed the go-kart, and I have regrets and anger at him for that. But at least I got to use it for a couple of years before he crashed it. So yeah, actually you're right. Yeah, I don't use it. Yeah, the golf cart he does not have a seatbelt actually. So oh man, I didn't see I had this code in here. This code looks so much prettier than mine, even though I wrote this. But I had this. I guess I made the same point last year with pretty colorful stuff. I said bad and good, I guess. But yeah, that's literally the same code that I have now. Yep. Should have seen that. My bad. Okay. No, what do you mean? That's not true. People wear seatbelts in Mexico. I was born there and was living there for a while. Although they don't use them on the back seats. Until I came to the U.S., I didn't understand. I thought that the backseat seatbelt was more of like there for fun. I just assumed that the cushion of the backseat would protect me in a crash. As a kid. Obviously, I'm a kid at that point, really young kid. But so that's true. Nobody ever uses them on the back seats in Mexico. So, but I do know here you get a ticket if you don't. So, I do tend to put them on. So, but when I do get family visiting, they don't put them on because they're like, oh, we just don't do that. I'm like, no, yeah, you should do that. I don't need a ticket. Yeah. Anyways, moving on to stacks and queues. Do I have? Let's see. Before I start writing something, do I have any pretty pictures here? This is kind of pretty, but yeah, this might be useful. I guess these were Legos or something I was using here. Maybe that'll come in useful for demonstrating. Stack. I might have to go to Mexico at some point in October for a little bit. So I might stream class from there actually. So I'll take my camera to the window and then we can see if people are wearing seatbelts or not. But we'll see. It will not disrupt you guys though because I have internet and everything there, so you won't. The background will be different. That's it. But that's not for sure though. I'm trying to see if I can avoid going in the middle of pandemic or Mexico is really bad state. But I might have to go, so no choice. All right. So okay. Stacks and queues. So this is another one that you probably covered in Tool 2, but maybe not. This one's more of a might have, not have. So I'll try to go more in detail about it. But yeah. Okay. So first of all, I guess let's use my little pictures here that I have to explain how stacks and queues work. So the way that I like to give examples for stacks and queues is the supermarket approach of lining up in line. Obviously for a supermarket is a queue, to pay. But when you're looking at an aisle and you have those inclinated aisles, when you go to the water bucket things, like a Walmart or something, and then they just have them like this, the chugs. They usually kind of have them all lined up like this, and then they use gravity to bring them to the front, right? And so whenever somebody takes something out, I don't know if the employees actually do it that way, but if they take something out, then this slides down. Whereas if you want to put it back, you push that up and put it in. And so that actually kind of represents a stack. So do we have anybody who has worked in the past in that stuff that can confirm or deny the rumors that they do this in dairy? I do used to, when I had more, I guess more time in my life, I would look at the milk and check the dates of like 4 of them before taking it. And I did notice that the ones in the back had better dates. So I don't think so with the dairy they do that, because they have rooms behind it that they can stock. I think it's only for the stuff that they can't stock from behind. That's like non-refrigerator stuff. Yeah, because it will stock from the back as well. So, but I think things like if you go to like the water where that they might do that. But yeah, so the best way to remember stacks and queues, let's just stick with stacks first, is the Lifo. So stacks are going to be Lifo, and queues are going to be FIFO. And what Lifo stands for is last in, first out. And what that means is that the last item you put in is the first one you take out. So the way stacks work is you have 3 operations. You have your push. Well, actually, you have 2 operations that are like the most important ones. And then you have one more operation that is typically thrown in, which is your top. But really, the top is just a combination of the other 2. If you're trying to just make a stack with the most bare bone things, you just need 2 things. And by the way, I wonder if the rocket took off. I think it's supposed to take off like right now. Let's see if 35 seconds for launch. You guys should. I can't really do this, but you guys can. You can put that on a side stream if you want, and see if it all goes well. Which hopefully it does, because there's people in the rocket, so it's not no joke if it blows up. But it will be okay. So yeah. Yeah, so we got push and pop, right? And so, again, let's analyze this with our 3 sort of rules that we have. We have insertion, we have retrieval, and we have deletion, right? And so push allows us to do that insertion, and then pop is a combination of retrieval and deletion, actually. So it kind of combines them both into one. All right, very cool. Rocket has taken off. Okay, so... So yeah, let me just, like I really do hope that most of you know at least stack and queue on the basic level, but just in case you don't, let me just run you through an example here with a little colorful cubes, okay? So we got a bunch of cubes and we're gonna store them in this bucket, this really long and thin bucket, okay? And so if I have a cube, what I'm gonna do is I'm just gonna throw it in. So it's just gonna fall all the way in. That operation is my push, and my push operation typically has a parameter in it, which is what I'm trying to push in, right? So like push yellow. So the T stands for yellow in this case, okay? And then from there, I have my other cube. So if I want to put something else, I push it in. So it goes here. Now, as you can see, because the bucket is very thin, there's no way it can like fall to the side. It just goes in like that, okay? And so that's my push. All right, so let's keep track of what I'm doing here. So this is my log. So I'm gonna push Y for yellow, and then maybe push, what color? Green. Okay? So now let's say that I wanna take out a Lego, okay? I still have 2 Legos out, but I wanna take out a Lego. There is no way for me, at least in a pure stack, to take out the yellow Lego because I have no way of reaching it. The only one I can take out is the one at the top of the stack. So the term top, when you're talking about a stack, is the next thing available. So that would be the green block. So if I say pop, what happens there is somebody takes the yellow block, well you take it out and then you just throw it into your play set, okay? So that will remove, so again, that's why pop is a combination of retrieval and deletion, because it will retrieve the top item and it will also delete it, okay? So it's a destructive operation. So it's one of those things where like it takes it out and throws it at you, and if you catch it, you're good to go. If you don't, it's gone forever. Okay? Yeah, I mean, queues are super easy to think about because anytime you make a line somewhere, you're making a queue. If we use stacks for making lines of places, people would like go up in arms and attack each other because like basically it's like everybody's always cutting in front of you kind of thing. Pop does indeed always return a value. That's the pure implementation of a stack means that this is going to return always a value, okay? And that's going to be what the top of the stack contains, okay? So Let's just kind of do a couple more of these to make sure we're on the same page. So let's go ahead and throw in some. Here they're just kind of on a table, so we can grab whatever we want. So let's go ahead and push two of these in. Push them in. Push, push. So we push red, and then we push green. Or sorry, not green, blue. Okay? Then let's pop something out. So we pop something out, we get a blue out of that. And we could pop things out. So let's say we pop two more out. We get the red, and then we get the yellow, and then it's empty. Okay? So that's the basic example of a stack. I don't have enough time to go into in depth about it. So what I'll do next time is I will go ahead and I'll give you an example of converting postfix notation. I have an example like that I could do. Otherwise, I'll just do some other example. But yeah, what I really want to do is I want to show you right now the complexity of the operations. So actually, I apparently have a table from last time, so I might as well put that in here and save some time. Okay, so we got our insert and our remove, which are kind of like our push and pop, but technically this is both removal as in retrieval and deletion, right? So it's a combination of both. So the beauty about a linked list implement, so here's the thing. A linked list and an array are actual implementations where you store the data. They're like ways to change how you store the data. Stacks and queues kind of go one layer above that. They no longer are talking about a specific implementation of them. They're just talking about a concept. So again, the concept here, it doesn't matter whether this is a bucket or programming or whatever. It's just a concept, right? When you're making a line, you know, it doesn't matter where you make the line. If it's an amusement park, at the supermarket, if it's you know, a queue for like pre-ordering something, it doesn't matter. None of that matters, right? It's a concept that we all kind of know how to work. So what we next need to do is say, okay, how do we take that concept and we implement it into programming? Well, there's a lot of different ways. We can implement it using a linked list. We can implement it using an array, or like a completely new different method that we could come up and design with, right? And so in our case, we want to see which of those is ideal. And it's always the case that, well, actually, in some data structures, there's going to be one ideal that's obvious, but there's always going to be some data structures where, like, some implementations of the data structures where, like, there's compromises, you know. Some things are good, some things are bad. And so, in the case of a stack, though, there is one obvious winner, and that is going to be that linked list implementation of it. Because with a linked list, you can represent the stack by just throwing something in the beginning and then removing it from the beginning for pop. And it's constant time for insertion and deletion, and you're all set. With array, it's constant time for removal as long as you take it off. And I'll show you a little bit more practical implementation next time. Again, it won't be code, but at least it'll be more like me drawing stuff. But I'll show you maybe some code. But you can kind of see, just thinking about it, that you still need to define a size for your array for the stack. And if you go over that size, you're going to have to rebuild the stack entirely again. So you're going to have to copy it over to an entire new array that's bigger, and that is going to take time. So that's no longer going to be constant time. That is going to be n, so it's going to be linear. So it's slow. Well, not super slow, but it's definitely not as fast as constant time, right? So that's going to be the disadvantage with the array. But if you have space, then yes, it will be just a matter of updating a little index that keeps track of the top of the stack and just throwing in the value, okay? So the clear winner here is going to be linked list for a stack implementation, and it turns out that for a queue as well. But again, we'll talk more about that next time, okay? At this point though, before I go any further, I would like to just stop because, you know, I do want to explain a little bit more in detail how to actually, you know, create a push and pop function. But I don't want to start that and then stop in 5 minutes, or 4 minutes actually now when class ends. Okay? So instead, I'll open the floor for any questions that you might have. So any questions about whatever we covered today? You're watching the rocket. It's trying to land now. Okay, like I said, hopefully a lot of the linked lists and stacks and queues is review. The only different new thing now is that you're starting to look at this in terms of asymptotic complexity, the O of 1, the O of n. But it's still relatively straightforward. You're not doing anything fancy, except for maybe like the binary search thing that I said was logarithms, right? So, yeah. Great. Well then, if there's nothing else, then that is all that I have for today. So, have a good weekend and, get going on the next assignment once that's released. It is already released. It's been released actually for quite a while now. Apparently, it was released on September 2nd. So, you still got a week to do it, but I wouldn't wait too long. So, yeah, just do it now. Just get it over with. All right, great. Well then, you guys have a nice day and weekend too, okay? Thanks for watching, everybody. I'll catch you later.